Okay, good morning. So welcome back. So we have 6 talks this morning, so 3 in the first session and in the second one. And we are going to start this morning with Crisan from Imperial College. And he's going to have a kind of dual talk with Colin Cotter later. And then Etienne Mémin after them.
Thank you very much. When Michael first approached me to tell me about this wonderful program that's been running since September, I jumped on the occasion because the timeliness for the program, it was perfect for the work that we were doing at the time when we've just finished at Imperial College. And this was a team of people that involved myself, Colin here, Daryl Holm, who I'm sure some of you already attended his lectures at the beginning of the program, and 2 our postdocs, Wei Pan and Igor Shevchenko. And that was because this could have been, this is essentially the perfect place to disseminate our work. So this is part of the dissemination of the work that we've done for the last 3 years, the 5 of us, and we use an EPSRC grant, an UK Research Council grant, to do that. That was somewhere in the region of £1 million. And so Colin and I were going to present the results of this work, but the time is very short, and we have 4 papers already out there. They are all on the archive, and I've enumerated them in here. And there's even more work that we sort of hurrying up to finish as we speak, and it will come online hopefully by the end of the year. So the work that we did for the past 3 years concentrated on 2 main areas. One was the development of stochastic geophysical fluid dynamic models, which were important in themselves, and sort of this they started from the first paper by Daryl in 2015, but they were essentially in the data assimilation, the development of the data assimilation methodology that we had throughout the project, because we used these stochastic geophysical dynamic models that we developed in order to perform model reduction. So this was part of our program. The second aim of this project was to apply particle filters in order to for data assimilations, for solving large-scale filtering problems. And we had 2 case studies for that. The first one was, and you can figure it out already from the title in there, for a 2D Euler model. And the first 2 papers refer to the 2D Euler model, the numerics and the methodology developed for the 2D Euler model. And the last 2 papers refers to another case studies, which is the 2-layer quasi-geostrophic model. I will talk very little about these case studies. The aim of my talk will be just sort of to describe, to give you the red line of our work, to describe the methodology, and to present in a sort of theoretical way how we look at data assimilation. And in particular, we look at data assimilation as a stochastic filtering problem. And this viewpoint is not new. As you've seen yesterday, Michael has advocated this for the last 40 years and perhaps even more. And it is somehow that the precepts, the principles of filtering have been embraced by the data assimilation community insofar as the linear filter is concerned. But somehow, somewhere along the line, the connection between the 2 has broken down, and when it came to try to look at the nonlinear part of stochastic filtering, somehow this is still seen as a rather exotic approach. And it is perhaps the right time to start looking at applying the general principles of stochastic filtering and look how methodology has been developed in stochastic filtering, not necessarily particle filters, but there are many other methodologies out there for solving nonlinear filtering problems, and that might have a benefit within the data assimilation work. So I will start by presenting the data assimilation as a stochastic filtering problem. Nothing new here, but it's really the right framework that enable us to sort of very simply and very straightforwardly start talking about particle filters, because particle filters have been developed as a methodology to solve general nonlinear filtering problem without having to rely on the linear filter or linearization techniques or control methods to solve to produce data assimilation methodology. And then I will explain how we did it, because for some time there's been some skepticism in parts of the community, mostly across the pond, that said that we cannot use particle filters to solve high-dimensional problems. And sort of people were detracted for doing that, and we were grateful for that because it gave us the time to develop this methodology. And so now we have developed this methodology. I'm going to show you. This is still at the beginning. This is still. I'm not saying that we've done it. I'm saying that we made a major step forward in develop methodology based on particle filters to solve high-dimensional problems. And I will explain how we did it. And I will present first sort of the standard particle filter, which is easily understandable and easily implementable. And then I will explain the add-on techniques that we used in order to make the particle filter work for a high-dimensional problem. And the problems, the two case studies that we looked at, each one of them had order of 1 million degrees of freedom. And I know that people that are working in operational laboratories, they say, okay, 1 million is not enough. We need 1 billion. But all we used was one workstation. We didn't have the liberty, the opportunity to use a massive supercomputer. So what I'm trying to say here is that there is scope here to raise this to the level of an operational system. And in fact, Roland Podcast for DWD has already done this. OK, so I will present the particle filter, and then I will spend as much time as I will have towards the end of the talk to explain how we use this introduction of stochasticity in geophysical fluid dynamics models to do model reduction. And Colin will take over from me in half an hour and give you more details about how this is done, why this was done, what's behind this, and tell you more about the case studies and so on and so forth. And I will conclude with some final remarks. OK, so this is I've given a course last week on data assimilation and particle filters, and this is the picture that I brought in right from the beginning, and I'm bringing it again. You know, in essence, this is the thing that says it all. And if people understand these pictures, this is sort of almost, you're almost halfway there to try to think from the perspective of stochastic filtering. So the picture is as follows. Let me describe the picture. We think of the underlying state, the truth, your weather, as being modeled by a stochastic process denoted by X. And in stochastic filtering, this is called a signal. And this process, this stochastic process, evolves in a state space, which is very, very high dimensional. You've seen yesterday the dimension of this space. This is not directly observable. what is observable, what we have at our disposal is a function of this process, and in the engineering community, this is called the sensor function. Now, then in the data assimilation community, we talk about observations operator and so on and so forth. So we have a function of the signal. This is the observation process. This models the data that is available to us. And normally, usually, we have this function observed with noise. This is the measurement noise. So what we model this with another process, y, which lives in a different space. And I keep repeating this. And you may think this is truly sort of a silly observation, but I've seen many people that apply this, and somehow people may think that the observation space and the state space are the same. They are not the same, and you need to think of them as being different. The dimension of the observation space, the dimension of your data is different, and as you've seen yesterday, it's somewhere of the order 10 to the power 6, 10 to the power 7. Now, that's the observation, and I write the observation here like this. Now, there is a continuous time equivalent of all of this. The signal evolves. What I'll describe next will be the discrete time equivalent of the stochastic filtering theory. There is a continuous time equivalent of that, where the signal is the solution of a stochastic differential equations or a stochastic partial differential equations, and then the observation will have this format. I'm not going to go into that. The entirety of my talk will rely only on describing the stochastic filtering as a discrete problem where time runs discretely 1, 2, 3, and so on. Okay, so we have two objects there. One is the state space, one is the signal, and one is the observation. And what you're interested in, we're interested in computing the distribution of the signal given the observation. So that's a probability measure. This is a probability measure. So you want to approximate this probability measure, which is the distribution of the signal given the observation. And the way in which I illustrate this probability measure is by this circle in this. So this circle is not just a point. This circle simply means that I have this probability measure here that sits on top of the state space and moves through the state space. Okay, so this circle is not just a point there, simply tries to illustrate, to sort of signify a whole probability measure in this 10 to the power 9 dimensions that moves through the space. Now, obviously, you might say, okay, but I don't really want the whole of probability measure. Perhaps I just want an estimate of the truth. But if you have this probability measure, by taking the expected value, the integral, the mean of this probability, that will give you an estimate of the truth. But you can get a lot more of that. You can get all the statistics related to the signal given the observations. So that's the stochastic filtering problem. You have a signal process, which is the hidden component. You have an observation process, which is the data. And the aim is to compute or find the conditional distribution of the signal at time t, given your observation. And in mathematical terms, that means that you want to look at the sigma algebra given by the observation and condition the signal with respect to the sigma algebra. Okay, so you have a very intuitive way to look at these things, but the mathematics behind this has been well documented and well finished so that you can understand from a mathematical perspective what you aim to achieve. And as I said, the way in which the discrete version of the filtering problem, there is a continuous version of the continuous problem, uses the language of probability theory. So the signal is modeled by a Markov chain, which has an initial distribution denoted by pi naught, and is described by the transition kernel of the Markov chain denoted by capital KT. Okay? And if you don't want to have this generality, if you want to have something which is very specific and clear and understandable, one way is to think of the signal as being a time series. The signal at time t is a function of the signal at time t minus 1, and then you have some randomness in the signal. You can think of that, you can think of this as being just a normal random variable, but you multiply this by some by some other function of the signal at time t minus 1. So it's a very simple way in which you can think of the signal, but you don't have to do that. The most general way is in terms of the transition kernel of the signal. Then you have the associated observation process, and the way in which you introduce the observation process can be very, very general, right? So you can say, well, the signal and the observation as a pair, they form a Markov chain. But the most traditional way and most understandable way in which you can introduce the observation process as a process is to say that is to describe the distribution of y given x, right, through a likelihood function through this function gt. So really the three elements that describe the evolution of this conditional distribution of the signal, this pi t, are the initial condition, pi naught, the transition kernel of the signal, and this likelihood function gt. These are the components, the bricks that are used to construct pi t. So you can see that I keep talking about pi t here. I'm not talking about the state. I'm not talking about the signal itself. So I'm focusing mostly on pi t, because once you know pi t, you can estimate the state, you can estimate any statistics with regards to the state. So if you want to know more about this, I've written a book some time ago on stochastic filtering. Most of the book is for continuous time stochastic filtering. There is one chapter in there dedicated to discrete time filtering. I invite you to look at it. I've written it as clearly as possible, and it contains the theoretical justification of particle filters. Now, you've seen this in many guises, and you've seen this already yesterday. There is a way in which you can very neatly write down the evolution of this conditional distribution, right? So this is the base formula, the base recursion formula, and it's very nicely written. Essentially, to go from pi t minus 1, i.e. the conditional distribution of the signal at time t minus 1, into the conditional distribution of the signal at time t, you go into by using two steps. And then you immediately see in data that this is really sort of parallel to what we think of in data assimilations, that you have a forecast step, and then you have an analysis step. And the forecast step, in this particular case, at the theoretical basis, looking at the evolution of pi t minus 1, uses the kernel of the signal, the transition kernel of the signal. So you evolve the distribution. You evolve this probability measure using the transition kernel of the signal. So there are ways in which you can think of this step, either the forecast or prediction, and you use the model. And then you have the nonlinear step. Yeah, I know, but I'm worried that this is okay. You have a nonlinear step where you take that likelihood function, you multiply this intermediate measure, which is called the predictive measure pt, and you multiply it by gt and normalize it to get to pi t. Okay, so this is a very nice and neat recursion which cannot be solved explicitly except in the linear case by the linear field in a Gaussian world, and that's the sort of the basis of the success of the Kalman filter, because in the case of the Kalman filter, you can solve this recursion formula explicitly. And if you cannot solve this recursion formula explicitly, one way to do that is to use particle filters. This is not the only way. There are many other methodologies out there for solving the filtering problem in the nonlinear case. This is the one that we used. Okay? So what is a particle filter? The particle filter is a class of methodologies that produce an approximation of the posterior distribution in the form of the occupation measure of a set of particles, of a set of weighted particles. So of course, you can, in the right language in data assimilation is to talk about ensembles. In particle filters, you talk about particles. They are one and the same thing. So at time 0, you start with an approximation of pi naught. You can sample n times from pi naught, the initial distribution of the signal. And in general, at time t, what you'll end up most of the time, you'll be a weighted approximation of the Dirac measure at the position of the particles. Okay? So how do you evolve the particles? pictorially, I'm doing this by straight lines. Essentially, you have a first step where the particles are evolved according to the signal equation. Then the particles are weighted according to the likelihood function, and then you can sample from the particles. And I have here a 2-page description of what I just said. You sample n times from pi naught, then the iteration from t minus 1 to t is done in 2 steps. As I said, you have the approximation at time t minus 1 as the linear combinations of equally weighted particles. Here I have Dirac measures, right? Then you sample, you move the particle forwards by using the transition kernel of the signal. You obtain an approximation of the predictive measure pt. Then you compute the normalized weights. So you take the weights coming from the likelihood function and you normalize. Then you have an approximation for pi tn. And then you sample n times from pi tn so that you end up again with a sample for where the particles are 9 minutes, 5 minutes. Oh God, where the particles are equally weighted. Now, if you try to use this methodology for a high-dimensional problem, it's not going to work directly. But what you do, and what we did, was to add on a series of steps that enable us to really succeed in applying this methodology to high-dimensional problem. And what we did, we used tempering, and we used jittering, we used model reduction, and nudging. So these are the 4 steps, the 4 add-on procedures that you use in order to succeed in applying particle filters for these high-dimensional problems. So the first step was, instead of doing the forecast step, in the forecast step we applied nudging. And for the assimilation of the data, the new data, we applied a combination of adaptive filtering and jittering. Okay? So I had here explanations of how you do the tempering. The tempering is done by flattening the likelihood function and then sampling from the flattened one and gradually building up to the whole likelihood function. This is an explanation of how you do the jittering. I just have to flash this in front of you. The nudging is done by modifying the signal distribution and by moving the particle forwards according to a different distribution that has an add-on drift that tries to put the particles closer to the truth, right? And then the model reduction, I hope, Colin, you'll have time to say a little bit more about the model reduction. So what I'm going to show you next, to just quickly conclude, this is just a simulation of, let me see if it's going to work. This is a simulation for one of our case studies. This is 2D Euler, right? On the right-hand side, you have the evolution of the velocity field. So dark blue means 0 velocity, and you can see the arrows in there. And sort of red means very high velocity. And on the on the left-hand side is the evolution of the vorticity. Okay? So what we did, we applied the methodology that I just described, and I'm going to just show you one picture, one simulation. So here, on the right-hand side is the truth, right? So this is the truth measured on a grid which is sort of a bit coarser than the original one that you've seen yesterday. And on the left-hand side is the conditional mean of the particles. You take the particles, you take the average of the particles, and you take the difference between that and the truth. And if it's dark blue, it means that there's very little difference between the truth and the conditional and the mean, the average of the particles. And if it's sort of dark red, it means that the difference is very large. Okay? So what you can see from here is that the results are quite encouraging, right? They are not perfect, right? Because we use very few observations. You use something of the order 100 to 200 observations. The size of the grid is somewhere in the region of 8,000, and we only observe the velocity at a fraction of the size of the grid. Now, what you should observe in there, that it's not the case. It's not the case that the approximation is perfect everywhere and at all places, but at any one place, the approximation is gradually the error gradually is sort of sorted, and then we move somewhere else, right? And this is really natural. We expect this to happen because this is a transport problem. The error is transported somewhere else, and then it's cleaned up there, and so on and so forth. There are situations where the error is really stationary, stays a lot in one place, and the reason for this is that it is possible that this is an area where the fluid doesn't move a lot, and sort of somehow the error accumulates in there. Particularly, there may be a problem if you don't have a lot of observation in that area. So if you don't have a lot of observations in that area to try to clear the error, then the error accumulates for a while, and eventually it goes away and it disappears. Okay? So I'm going to stop here. I have a lot more to tell you, but I can't. I'm going to wait for your questions, and then I'm going to let Colin continue the presentations of our project. Thank you.
So, yeah, Peter Jan.
Well, perhaps this is not for recording, but perhaps a historical perspective slightly. So this stochastic filtering has been known in the data simulation community for, I'd say, at least 25 years, right? I mean, there were papers by oceanographers who did that stuff.
Even more.
No. I mean particle filtering also, right?
Oh,
so
yeah.
We did that stuff, and the reason it hasn't been taken on is very simple: that we didn't manage to get it to work, right? I mean, there are many papers about trying to get particle filters to work, and it's just extremely hard. And so it's great that this is happening, right? That you guys are coming on with new ideas to make this work. And long way to go, but we're getting there.
Right.
Thank you for the talk. Now, can you show again the last slide?
Which one?
With the Euler simulation.
The refined grid or
the error? The error.
The error.
The two dimension. I just wanted to know if the error is normalized there or it's the absolute error.
It's the absolute error.
It's the absolute error.
I'm just giving you as it is. I'm not cheating, right?
Okay.
So this is that's what we get. You get the so this is the difference between the magnitude of the velocity and the magnitude of the approximate velocity. I can't give you more than that.
Okay, so
on the other side, you see the actual arrows that tell you the magnitude.
So do I understand correctly that it's, in many places you have an error that is of the order of 100% on the truth?
Well, not really, because, it's, so the error is very close to zero in most of the places, right? You can say that, of course, the error is, the velocity is small in many of these places, but this isn't, it's not a universal thing.
So that's why one should maybe normalize it. It should be better to normalize it with the signal, right?
Yes.
To see, because the error might be zero because the signal is zero.
And the picture that you'll see will be similar, except you'll have, I can give you more colors if you want.
No, that was a...
Question by Idris.
Hi, Dan. If I understood you correctly, you started with initial data with some distribution.
Yes.
Then what do you call the truth? What is your definition of the truth? Because there is distribution of truth.
Yes. So we have, Colin, are you going to cover this? So we have one realizations of the deterministic Euler equation, right? Where we start from a position where somehow the solution has reached the attractor, in the sense that we start from somewhere which it's really a very sort of theoretically described through a sort of function which involves trigonometrics functions and so on. We run it sufficiently long so that you get to one positions where it looks natural, the things that Colin will show you what is the initial condition, and then we run this on the grid, on the high-dimensional grid, which has 500,000 points for a long time. Now, the questions that you I think, want to ask, you say, okay, but now, when you start from the particles, you shouldn't start from the truth. And the answer is yes, we don't cheat. We do not start from the truth. So what we do, we get a perturbation of the truth in a very natural way in which we can advect the truth by using past velocity fields for one step. So that's how this is where we start from. This is how we initialize the particle filter. So the particle filter is not initialized from the truth. In fact, we specifically take the truth out of the particle filter, initialized from a distribution that, it's really close to the truth. Does that answer the question?
I still do not understand your definition of truth.
The truth is one realization of the Euler of the solution of the Euler equation on a high-dimensional grid. That's the truth.
Like you do in the real world, right? You have one atmosphere, one realization of what the atmosphere is doing. And he's just mimicking that in his experiments. What's the difficulty?
Why would you not accept this as a realization?
I thought that we started initial data with distributions of initial data. So therefore you have to go with the truth is all the distribution and then choose one of them.
Right. So this is how you do it when you do the particle filters, but the truth is one realization. This is only one way. Weather is one. There's no more than one realization of the weather. So we have to have the truth as being that. Thank you.
Okay. Thank you very much. Thank you very much, Dan.
Yeah.